Let's look at applying what we know about force and stress to figuring out whether welds are strong enough. So just to review where we were in the last set of slides, we talked about groove welds, which take tension and compression, and fillet welds, which take shear. We mentioned that the calculations are done by engineers, so you shouldn't feel that the responsibility will be on you. It absolutely won't. But it's good to know what are they thinking about. So they're using these two standards. And you might remember from another discussion we had that AISC typically uses a safety factor of 1 2/3, 1.67. So ultimate stress over allowable stress is 1.67 in structural steel. And that works out to an allowable stress that's 60% of the ultimate stress. And you see that over and over again in the steel book. All right, so fillet welds usually fail in shear. So it's shear stress that we'll look at. And here at the bottom, you can see a diagram illustrating a fillet weld being pulled apart, being sheared right down the middle. And it's shearing right down the middle in the part of the weld that has the smallest area, which makes sense. So here is a close-up view of the end view of a weld. This is a fillet weld, so it's shaped like a triangle. And the area that has the shortest distance across the triangle here is called the throat. Here is our book illustrating what a throat is. That's where the weld will fail because that's the smallest size. So how do we figure out that size? Well, think about 45-degree triangles where the two sides are equal and the two angles are 45 degrees. And let's say you have a 45-degree triangle where the hypotenuse is 1. How big are the short sides? You would find out they are 0.707. Well, that's lovely, but our weld is sitting like this. So let's rotate this 45-degree triangle like this. So now it matches the way the throat is sitting in a fillet weld. And now, if the length across the hypotenuse, the length across the bottom is 1, then that short side, right here at the throat, is 0.707 as big. In other words, the throat of a weld is 0.707 the size of the weld. So if this were a 1-inch weld, this would be a 0.707 throat. All right, so with that, we can calculate stress. Using our good old stress formula, stress is force over area, pounds per square inch. And we'll find the area using that throat distance. Here at the bottom of the slide, I've colored in. This weld has been sheared right down the middle, and I've colored in the fracture face along which that weld has sheared. So the area that we'll plug into our stress calculation, pounds per square inch, force over area, the area is the area where that weld sheared. And there's one on each side, isn't there, if you've welded on both sides. So it's the height of that place times the length of that place, times 2 if you've welded on both sides. And that throat, again, just to repeat, that throat is 0.707 times the weld size, the leg of the weld. Okay, so in the quiz, we have this plate with a fillet weld. It's got a 9-inch long fillet weld on each side of this plate that's being welded to a bigger plate. Those are 3/8 inch fillet welds. They're using electrodes that have an ultimate tensile stress of 70,000 psi. And this connection is being pulled on with 100,000 pounds of force. Two questions. How big is the stress in these welds? And are the welds adequate? That's what we're going to figure out here. So first of all, if you've got a 3/8 inch weld, what size is the throat? Here's an end view of the weld, and it's 3/8 of an inch across the leg of the weld. So that means, there's our triangle. If it's 3/8 across the hypotenuse, then the throat is 0.707 times 3/8. Now how about the area? So if we're welding on both sides on this connection, we have 9 inches on one side, 9 inches on the other side, for a total length of 18 inches. And the throat across here, if you say 3/8 times 0.707, you come up with 0.265. So this shear face on one side is 9 times 0.265, and there's one on the other side that's just the same size. So the area of the weld that's getting sheared is 0.265, that's the throat, 0.265 times a total length of 18 inches. So you are going to have a total area of 4.77 square inches. Or if you prefer, and I kind of do, I like to think about, okay, there's a 265 times 9 on one side and a 265 times 9 on the other side. So I say 0.265 times 9 equals, and then I say times 2. And I still come up with 4.77 square inches. Now let's figure out what is the stress. Well, from here, you might find this a little bit straightforward. The force pulling on this thing is 100,000 pounds. You just figured out that the area is 4.77 square inches. Yay, we can use our stress equation. Stress is force over area. There's our familiar triangle. So stress is force over area. We've got a force of 100,000 pounds and a total area of 4.77. And if you punch that into your calculator, I bet you'll come up with 20,964 psi. That is the amount of shear stress in those welds. Every square inch of weld is experiencing that amount of stress. Okay, so last question, are the welds adequate? What do we do here? So we know that we're using welding electrodes that are rated at 70,000 psi ultimate stress, and we're told that we're going to use a safety factor of 2. We're trying to find the allowable stress so that we can answer the question, are the welds adequate? What are we given? Well, we know the ultimate stress of those welding rods is 70,000 psi. We just figured out that the actual stress in those welds, in the previous question, we just figured out that those were 20,964 psi. And what else? We know that we have a safety factor of 2. So what equation can we use? We can use our factor of safety equation. And you might recall back when we talked about factor of safety, we used one of these triangles. So the safety factor is ultimate stress over allowable stress. Ultimate stress over allowable stress. So let's find the allowable stress. Well, what do we know? We know the ultimate, we know the factor of safety. We're trying to find the allowable. We could cover up this part of our triangle, and we'll find that it's ultimate stress divided by safety factor. Or we could do our good old shortcut, where when we have three terms in an equation, the one on the bottom and the one by itself just switch places. We'll come up with the same net result. I like to do that, the old switch places thing. So we come up with ultimate stress divided by factor of safety gives us allowable stress. Great. So ultimate stress is 70,000 divided by factor of safety of 2 gives us an allowable stress of 35,000 psi. That's how much we could allow. Are the welds adequate, you ask? Well, let's see. The ultimate stress is 70,000. The actual stress that you figured out, you calculated this, the actual stress is 20,964 psi. So what? We have a safety factor of 2, don't we? So we have an allowable stress of 35,000. What do we do with these numbers? We're allowed to have a stress of 35,000. We only have a stress of 20,000 something. 20,000 something psi is less than 35,000 psi. Therefore, yes, this weld is adequate. And engineers sometimes use this triangle made of 3 dots. That stands for therefore. And engineers will sometimes write, therefore, okay. Some engineers use these dots and some don't. These, if you ever took a classic geometry class where you used logic and you wrote proofs, you used those dots a lot. Well, anyway, so we just found out that, yes, 20,000 is less than 35,000. Therefore, this weld is adequate. Another time, if you were really, or your engineer were really, getting serious about this whole connection, you would still need to investigate the base metal, the steel plates themselves, to find out, can they withstand this load? So you'd want to know how big is the area of the plate. If it's mild steel, you'd want to know the yield stress, and you already know that, don't you? The yield stress of mild steel is 36,000 psi. You'd want to figure out, okay, what is the allowable stress if you're using a safety factor, and then you'd figure out what is the actual stress on these particular plates. So there's a whirlwind tour of figuring out some stress in a fillet weld.